Okay, so last time we added the concept of time to the game and had this like little spinny clock when we held down space. And when we let go of space, it goes away. And what we were talking about over here was sort of introductory calculus. And oh, that's really zoomed in. Can I zoom out, please? So what we had done so far with that was simple integration and differentiation. So if you recall, we did if we have a function f of x equals, what do we have, 7x to the third, etc., etc. If we integrate that, we get f of x, and then we have to do this, we multiply that 21, and then x, oh no, sorry, I'm going backwards. This is why it helps to actually have the example that I had up before. What are we doing? Yes, okay, if we differentiate that, f dash to the x, we get, we multiply that way, 21, and subtract 1 from the coefficient. Whereas if we differentiate, if we integrate, we divide the coefficient by the exponent plus 1. So it's that's 3, 21 divided by 3 equals 7, and so on. So that's what we got through. And we were pretty comfortable about that, and sort of the idea that if we have a graph, if we integrate, we're getting the area under the graph, and if we differentiate, we're getting the tangent at the graph of the graph. So that was all of the calculus that we did. So we're all reasonably happy with that.
Yeah, I watched chapter 8, and he used the term anti-derivative. Is that the same thing?
That's the same thing.
As a differentiation, I guess.
I'm trying to recall. I'm not sure I can really recall sufficiently what the difference between integration and anti-differentiation is. It's like a minor technicality, though.
Okay.
So it's basically
for what we're doing. Doesn't really factor into it.
So
There's
in
not
fact,
a third method.
I suspect what it is we're differentiating this way, and we're getting 7x to the third becomes 21x to the 2. What we're doing here is an antiderivative, and this is, I could be wrong here, but I think it is. This is not actually integration. This is an antiderivative, and then I think if we stick the the plus c on there, then we're actually integrating. I think.
Okay, so actually it'd be more helpful for me to just continue to think of it as integration, as in getting the area under the line. Otherwise it'll just get complicated.
Yeah. So, and then of course we had that thing where it's we get this function out the other end when we integrate, and it's well, is it that, or is it is it that, and we have this plus c concept. That's right. So yeah, so we covered that pretty well, and you watched those 3 blue, 1 brown videos, so we're all good with that. So then we get to some physics. So basically what we have is position. We want to know the position of something at some at some time t, and one way we can do that is if we have a velocity, we can integrate that up to get a position, and by the same token, acceleration, we can integrate that up to get a velocity, which we can then integrate to get a position, and we can also differentiate the other way down. So if we have a graph showing the position of our object, we can differentiate that and get the instantaneous velocity at any position. So that should also be fairly well known at this point. So you happy with that?
So far?
Excellent. So let's actually do some of this now. So what we're going to do, already, and I'll start using the standard physics symbols for this. We have a position S at time t equals S0. And this is what we have in the program. So if I come back to this little fellow and I hit run and we drop in a shape, this is a shape, and it's at, I'll start this little clock going, and at every time t, it's got this one fixed position. So position at time 0 is its position at all times. And so that's just dead obvious, and we can find the code for this.
Mine's at the very bottom of the
am I on the right thing? Did we talk about this on stream or not? I think we talked about this. I can't remember if we'd stopped the stream or not. So we have, okay, this is where we're drawing the shapes. And we've got the separation down here. So the way we're getting the position is shape.position in this case, and shape.position, shape.position. So we've just got this fixed position now. What I did want to say, we have two ways of actually handling physics in the game. We have the parametric method, and we have the what do we call it? The iterative method.
Right. Parametric is the sort of the sampling one where you don't have state, and iterative is the one where you are retaining state.
Exactly, and I think we did talk about this one because I remember drawing this graph where it's like and so we've got frame boundaries here on the iterative one, and the concept that I was trying to get across is like if you do this inaccurately and you just consider, okay, we've got a position there and a position there on the frame boundary, you'll start to accumulate errors if you don't consider the fact that the individual lines between each frame could be curved, and so we actually, if we do the the integration and the differentiation properly, we can actually account for these curves in a more accurate way and get a more accurate result out the other end. Because
right, as opposed to disjointed instant changes to position or speed and that kind of thing too.
Pretty much. So I mean, you're only going to see what's on the frame boundaries, but over several frames, I know I just fixed my diagram to actually show this, but we accumulate this error here. So you can imagine you could get quite different results depending on where things line up on the frames, which is sometimes it doesn't matter, but sometimes it does, particularly if you're doing a physics heavy thing.
Does this count in pixel games? Because I'm wondering if you can even accumulate error with an integer if you're going to do pixel based physics. Would this still be a problem, or would this be something that you could get away with because the rounding would kill any slop?
we actually absolutely we did. So obviously we had an iterative thing because you've got player input and stuff to handle, but we actually have, and I'll show you the code for this. Do I have a link? I think yes, I have the link, so I'll show you this later. But there is I'll show you it later when I've actually done the maths. So I can be like, yep, and there's the maths in the thing. But we actually do this same sort of thing in River City, and what we do two things there that are not really related, but you kind of mentioned both of them. One of them is we actually track some fixed point precision. So in River City we have this one I will show you if I can get the code up, if I can find my web browser. One sec. Just create a pixel 3D. Okay, so this is the part where I have to actually find the code. Engine and physics. I'm going to guess it's in physics. Might have to search for it.
Probably need to reorg some of this. What class are you looking for?
Packed velocity. So found it. So this is packed velocity, and so this is actually a fairly complicated structure. So it's only 4 bytes long, and I'll just draw out what it does. So it's like int packed view. It's scrolly. And this is divided up into, 4 bytes, and we actually pack values in here. So what the expectation is if you have like this packed velocity structure, is somewhere else you've got a position. Actually, I'll just pretend it's one-dimensional for now. So you've got some other class, or actually somewhere else in the class you've got this position as well. And so this tells you in 4 bytes where you are in world space. So this is like just obviously a position, and it's rounded to the pixel grid. So that should be fairly straightforward. The packed value here packs a few things. It has 3 bytes of actual velocity, which itself is divided into like whole part and so this is a fixed precision value, so it's got 16 bits of whole part and 8 bits of decimal part, and it also packs in I'm running out of colors, that one. a decimal for the position. So this actually becomes a 5 byte value when you have a velocity associated with it. And so this part tells you where you are in the pixel grid, but this part tells you, where you are inside an individual pixel down to, 256 possible offsets within that grid. So that's how we kind of accumulate the error, is what you'd probably say.
Okay, it's basically going into that blue bucket.
Yeah, exactly. So that gives you that extra precision that you kind of need for this sort of thing. Because if you have a really low velocity, like the whole point is, if you have a really low velocity, say a entirely decimal velocity, because if you recall, our velocity is measured in pixels per frame rather than like a traditional one, which would be like meters per second. And I think we talked about this, and it's like meters per second. If you're just working in floating point, you just do this and call it a day. Whereas here we're working in pixels per frame. And so you can imagine if your thing is like 0.1 pixels per frame, it's like what that actually is it's 10 frames per pixel. And so every 10 frames you want to move from from this pixel to this pixel.
Right. And it would be disastrous to you couldn't cut that to 0 or to 1, because both would be terrible results.
Exactly that. And so you have to have some kind of way of counting up, has it been 10 frames yet? And obviously 10 is probably going to round to like 0.9, well, so I don't know, 0.095, whatever. But still, it would be close enough.
Cool.
So that's how that works. And then the code for this is, in fact, I think I'll probably end up looking at this in more detail later, but we get out the velocity in 24.8 fixed format. So that's where shifting it up by whatever the shift is, and then we're masking out the position. Okay. Oh yeah. Sorry. Well, I've got that backwards. Yeah, we're shifting it down. That it shifts this off the end, so we just get back this red bit when we get it out, and then when we set it, we shift the value we're inserting up and make sure we include the existing position, and then we that's the whole part of the velocity, and we can scale the velocity, so that's just a fixed point multiply. And this update thing is what we'll talk about, because that's where the calculus thing happens. And then we also have a bit of maths there that's also related to what we're doing. So let's go back to talking about this thing over here. So are you happy with all this?
Yep. It sounds like it'll be easier to think in meters per second for now, and that's sort of like an advanced.
Yeah.
But I mean, I totally get what's happening.
Yeah. So this is just it's the same thing, but it's where we're packing it and bit shifting it and quantizing it to a pixel grid and so on. But it's exactly the same concept. Certainly the physics part. So this is what we have now, and this this is so obvious it's not funny. It's like it's always at the position it starts at. So let's now say we want to start adding in this thing, and this is where we start doing some integration. So let's say we have an initial velocity, or we have a fixed velocity, and we're going to say velocity at time, I keep writing f there, time t equals, and I'm going to use again the sort of traditional physics symbol for this, u. So u is going to be our initial velocity, so you could also think of this as v0. And what we're going to do is all right, we have a fixed velocity, so it's like we're this shape and we're moving at a fixed speed, and we're going to integrate this up to get s of t. And so then we do this thing we were talking about over here, and so we're integrating this way, and so what we need to do is we can say, all right, that u is actually u t0, and what we get out the other end down here is s of t equals u t. And so we're adding 1 here, and then what is it? It's dividing. I think it's dividing. Yeah, we're adding 1, and then we're dividing u by 1. So let's draw that in. We add 1 and divide u by 1. So it's s of t equals ut. So that's should be really obvious at this point, and you can sort of think it's like, okay, well, at time 0 we've got none of the velocity, but at time 2, if we're moving at 2 meters per second, and we've had 2 seconds, we've moved 4 meters, and so it's 2 times 2 is 4. So that should be super obvious what we've got here. So does that make sense?
Yeah, I mean the nomenclature is throwing me a little bit, but I mean, I think that's fine. I mean, this function is pretty simple though, right? There's no curve in this. This is just
exactly. So this is going to look like this. Now I have missed a bit, and that is we have to do the
constant
plus c, and
is that the current position, or is that?
Well, that's the starting position. So we end up with
Right.
We've got S0 here, and so rather than going plus C, we're going to go plus S0. So
is this in that we don't have? Do we have to translate that? This is just in theory, so it doesn't really. There's no basis to convert this to, right? The position specifically. We have, sorry, it sounds weird. What I mean to say is we have a position that's in world space, so we don't have to think about doing any like normalization or changing bases or whatever when we put this in here, right? Because it literally doesn't matter. It's just going to be added or subtracted from the end.
Exactly. So this is all in world space, and we can also do sort of a unit analysis on this. So it's like, all right, velocity is in meters per second times time, which is in seconds, plus meters. And so what you'll find is obviously the seconds cancel out, and we have meters plus meters. So
but meters is you're saying S0 is meters, not XY.
I think I understand. Okay, so this is all, the way these work is they're all effectively one-dimensional. And so if you want 2 dimensions, if you want an X and a Y...
We'd have to differentiate?
No, we basically just do it twice. So what this becomes is, I'll do it over here, is...
I think you mentioned this earlier a couple episodes ago about how we have to do it twice, but I missed it.
That's all right. So I'll just write it out because it's like... And it's like SY T equals U Y T plus S0Y.
Right.
So it's they're wholly, I don't know, I'm not sure the correct terminology, but they're unrelated effectively. They're each axis
orthogonal?
You handle on its own. Sorry?
Orthogonal?
Orthogonal? I think that might be I think it might be correct. Orthogonal. We'll take orthogonal. So they're orthogonal.
Got it.
So now what we're going to do is we're going to take this, but I mean, that was a good question because also this. But the thing is, we can do, we have our nice vector type, so we can do things like, okay, here's our xy, here's our xy, here's our xy. So it's like, oh look, we've got vectors and the same formula, so we can actually do this with vec2. So we're going to actually just code that up real quick. So, and what we're going to do is we're going to code up this fixed velocity thing, and because we're doing it in this parametric way rather than iterative, we don't actually have to store any state, so we can just do this in the draw method. So this is entirely functional.
Cool.
So and we were talking about that before when we were talking about the what was it, the separation method. We calculate separation is now a sort of a functional method, and so we can just do it in the draw step and draw the result. So we're going to do the same thing here. So I'm going to hand this over to you, and just about here we have our what have we got? We have time that we added over here. So that's what we'll use to keep track of when we are. And I'll let you pick what velocity we're going to set, but I think we're vaguely in pixels.
Yeah. So what are we drawing? We're drawing
So
like
yeah.
Like, yeah, I mean here we're drawing the circles and whatnot, but and we have a time, so S of
Okay.
What are we going for here? We want to draw we're not gonna move it, I don't think.
We're not going to change the position, but we are going to animate it basically. So we're making an animation is effectively what we're doing. So as time changes, we want the position that we're drawing it at to change.
Right.
And so this block of code is where we're going to focus, and we may need to be like, all right, we've got position. We might need to separate that out, like bring it up here. So over to you.
Sometimes the helpers are worse than just doing it. Alright. Oops. Ah! Alright. So there's my vec2 position. And I have time, that's float. Oh, I want to draw, say, Yeah, okay, so we wanna manipulate the position by the time. Uh, S. What's that? Wee. Okay. Well, don't want to do this. I'm about to do it anyway, though.
That's all right. Try
Um,
it. Try. I mean, try stuff out. It's always.
yeah. I'm just starting here. This is bad. Well, actually, I don't know. Sorry. I mean, two things are happening. We have two axes. I'm trying to do this on the like this is C, right?
Mm.
So this doesn't matter. This is stupid, but this isn't anything. Like we can't just add the distance.
Well, this is
Where's the distance? There is no distance yet.
so. This is where this thing that I was doing over here helps, and that's unit analysis. So what you've kind of done there is you've added what is basically meters to seconds. So meters plus seconds is kind of a non sequitur.
That's right. But I'm missing the acceleration that would give me
we,
the
we haven't done
velocity.
acceleration yet, but that's
I
okay.
don't have. Yeah, but well,
So
I don't have a velocity because I only have a time and I have
okay,
a
so
position.
so what I want you to do is vector2 velocity equals mu, and then make up a value. So maybe we go sideways, so like 5, and we'll see if that's too fast. So maybe that will help.
Right. So this is meters per second. So I mean, oh, hold on. What did I do here? I did that stupid thing that happens with a vector when you try to scale it. Yeah, I'm scaling it. I don't think I'm supposed to be doing that.
Well, hold up. So what, as I was saying with a sorry, I just lost my train of thought. With the unit analysis,
Yeah.
what you have, so this float here is obviously a bug, which the compiler's telling you about, but meters times seconds, or sorry, in fact, that's not even meters times seconds, which although meters times seconds can be valid, this is actually meters per second times seconds. So that's actually okay. And you end up with meters at the end of it because seconds cancel. So,
Yeah,
and this is fine too.
My biggest problem is this these math variables u and v and t and s and m and whatever.
Okay.
Makes it hard for me to map.
Okay. Well, that's all right. I do want to get us used to using those variables, so we'll have to stick to them for now. But yeah, u is initial velocity.
Right. Okay. So I'm gonna try to do that.
Okay.
I think this is u. This is obviously t. I'm even gonna do this silly thing here. Pix. And this is wait, u is initial velocity, right? And this is s0.
Yep.
And this guy, this is well, I don't know if there's two of these. I think there is because there's two orthogonal axes. What is u? U is the initial velocity, so this is going to be meters per second times seconds, which gives you meters. So this is meters,
Mm-hmm.
and this is meters, and this is initial position in meters on each plane. So I think I'm okay right now.
So not too bad so far. What I want you to have a quick think about is this line here. Perhaps just comment this one out and just maybe try this one again because that one's kind of wrong. So just drop that one down a few lines and ignore it for now, and just try that one again.
Okay. Well, S0 is my C. It doesn't matter. So, can you bring back the
diagram? Certainly.
Yeah. So I just have a hard time looking at this and making sense of it. So I mean, simple in concept, and then I go and do it. So I mean, I'm just gonna. I mean, yeah, U times T plus. There's my constant. The constant is the thing that doesn't matter. U is the initial velocity, multiplying it by time. That's this and this. So this is just for one axis. So that's basically this. It's that. And then, okay, so what if instead of doing it like this, I do it like... I mean, that's unfortunately exactly the same thing. Let's just flip it around.
So what I'll point out real quick, let's just insert a bunch of new lines just above your comment here so we can get a bit of clear space. Let's just drop that down so we have some space to think about this. So just focusing on these two lines here, what I want to show you is that we can look at this and we'll be like, all right, we have this t is a single dimensional value that we're multiplying. So we're scaling by a scalar.
Right.
And then this one here, we've got x and y, and coming out the other end, we've got x and y. So what we can do here is vector2.
Make a vector.
Distance equals u times t. So we can actually combine that. So while sort of on a lower level, these things are separated like this, you can actually think about them as a single method like this and not have to worry about what the different axes are doing.
Yeah, I thought about that. I missed that the vector2 had that implicit.
And one of the ways you can think about this sort of usefully is the same way we were doing meters divided by seconds times seconds. Is it's two-dimensional meters divided by seconds times seconds plus two-dimensional meters, and then at the end you get two-dimensional meters because you can just add the two-dimensional meters up. So it's the same unit analysis will work with dimensional analysis.
Okay. Well, I mean, okay. So
over you. You got rid of the S0.
I did because all it did was, I mean, all it's doing is this, right?
So I think you're kind of on the right track by basically writing, like if this is the formula you have, writing that formula out in code is a reasonable thing to do. So I think you're on the right track by being, all right, we'll make this t, we'll make this u, we'll make this S0, and we have those things, and then all we have to do is just finish that up, basically.
Yeah. Right. Like that's.
Mm-hmm. That looks pretty good to me.
The only thing is, that's not, I mean, I'm not changing. This is, like you said, parametric, so I'm not mutating any state. It's just adding.
Mm-hmm. So,
not sure about this though, because this is already accounted for here.
Exactly. So you've added position twice, effectively. But if you do that, then that's correct.
All right, and then same. Where else? I gotta put this somewhere else, right here. That took way longer than it should have.
No, sorry. Okay.
Yeah.
Okay, so let's run this and see if it does what we expect to begin with, and then we'll look at maybe cleaning it up a bit. But it's already pretty clean. So make a shape. I'll let you do the honors, and hit space and see.
I repaved my laptop and it's still the slowest thing in the world. All right.
Hey, off it goes. 5 is maybe a bit slow, but
Yeah,
it's working.
it is working.
Excellent. Okay, and so that's exactly what we wanted. And we can now change. We can be like, okay, let's make this a bit bigger, so we get some oomph into it. And maybe we'll set this like 25. So we can now set an initial velocity, or a velocity, and now we have this formula that moves stuff around, which is exactly what we wanted.
Cool.
And so you can imagine that's going to be like, if we expand upon this, that's going to be really useful for even just like general animation, even if we're not colliding stuff. It's like if we have like a user interface or something, we just want the buttons to like scroll out or something. Be like, all right, we'll give them some velocity and off they go. So now I have
interesting.
Yeah.
The kind of sort of, you probably can't see it with streaming and whatnot, but it seems like I don't know what the right word for it is, but just like you can kind of see the edges of that circle kind of either blurring or kind of like flipping in and out of clarity on the edges. Is that like just a GPU thing?
Well, let me try it online.
You do it with fine shapes.
Well, oh yeah, I think I understand what you mean. And so what's happening there is like it's a pixel alignment thing. Hang on, let me see. Okay, so what's happening is if we have a pixel grid, and say our circle is centered like here, we're going to end up with like that, more or less.
Right.
This. And the way our circle renderer works is it's going to be like, actually it's more like this. It's like Andrew can totally draw a circle. Okay, and then what our circle renderer does is like, all right, all of the pixels that are touched, it's going to fill those in. And we get this, like, in this case, because the circle's tiny, we get this like blob shape. And then when our circle moves a bit and we go over like here, then all of a sudden our circle is going to be like this or something. And what was going to happen is we're going to end up with like this square and this one and this one and this one and this one and this one, and that's a very different shape. And I know I've drawn that very roughly, but we've got these little jaggy bits sticking out the sides, for example. And that's basically because we're now doing this thing where we're moving. Well, what did we write? We were at 50 units per second, but every frame we're adding 1/60th of a second, so it's like 0. I forget the exact value, so 1666666, and so we end up off the pixel boundaries almost immediately.
And this is probably why we're doing the quantizing in River City, right? So we can do something smooth, because this circle is like literally shimmering when it moves, and I'm like, this can't be the state of the art. Like, I'm sure we could make this smooth, but that has a lot to do with like optimizing it to fit in those spaces so we don't go sub-pixel, I guess.
Yeah. So what we do in this particular case, if we wanted to get rid of the shimmering, the easiest way to do that would be to add some anti-aliasing. So rather than having like a hard boundary around this shape that ends up like that, we'd have this is the most amazing circle. You know, we'd like have some intermediate values. So it's like that one's going to be slightly lighter, like that, and
That's right.
then, you know, these ones might be, you know, darker in the middle, and that would not completely get rid of the problem, but it would get rid of it enough so, like, sort of visually it would probably be acceptable for a game. If you were like really super concerned, certainly if you were making a pixel based game like River City, you would have to pixel align it, but that becomes tricky because as you know, what's happening is we're drawing a shape, but we have this camera, we can like drag it around, we can zoom it in and out, and so where the pixel alignment's going to end up also depends on the camera. So we'd have to actually consider the camera when we did the pixel alignment. So that's certainly possible, but it's a bit more challenging mathematically.
Right. Okay.
So let's now we have this here. Let's just if we go back to the code for a sec. What we might do is let's get rid of this d, because that's sort of not part of this formula. I think it's probably worthwhile. And so I just want to sort of clean that up just a smidgen. And the other thing, sort of a traditional maths notation, is you probably wouldn't call this st, you'd probably just call this s, because it's the t is kind of implicit in the fact that this is the position. And I mean, I guess, yeah, the fact that this is a function that takes time as a parameter, it's sort of unusual to notate it that way. But that's just a notation thing. Otherwise, that's pretty good. So let's just finish up by doing one more of these things. So what we had over here, we had an initial velocity, and we integrated up to get a position. So if we have now initial acceleration, keep doing that, acceleration at time t equals some constant, and I'm going to use traditional physics notation again, which is going to mean that this is going to be acceleration equals acceleration. Then we're going to integrate up. So we're basically doing the same thing as we did here, but we're going to do it twice. So this one's easy because we've more or less already done it. So if we integrate it up from acceleration, we get velocity, so does that make sense? Sort of as time goes on, we accumulate acceleration, which is, you know, meters per second per second. So we end up with acceleration is at plus, you know, just like we had this initial position here, we're going to have this initial velocity, which we already have a symbol for. We have u. And then if we integrate up again, we're going to get position at time t equals, and this is useful. I just want to say that this is useful on its own. If we have like a animation that's like, maybe we have a square and we want to know if this square is like moving along, perhaps we animate it like, you know, we add some, you know, that to it, or we add like some lines coming out the back and stuff. So actually knowing the velocity is useful in itself, but obviously we want the position. So integrate this up again, and we get, you know, this is 1, so we add 1 to it and then divide, so we get half a t squared plus this one becomes u t plus s0. So are you happy with that little maneuver that I just did there?
Yeah, I mean, I've seen you do it I've seen you do it before. I know that when you're I remember from our last couple of sessions that when you integrate that third time, that's when you add that constant. I know that you go the other way, you get rid of it.
So it's not so much it's not so much the third time we add a constant. We're always, every time we integrate, we have to add a constant. So this is the constant we're adding here, and this is the constant we're adding for like here.
Right.
And so this constant that we've added, it stays there, and we actually have to add a time to it as well when we integrate the second time.
Right, you're adding a dimension.
Not so much a dimension, but it becomes time dependent, I guess. Because it is exactly what it says. It's like this becomes your starting velocity, and then as we know from here, if you have a starting velocity and you want to position that velocity is going to always be there. So that changes the position. Like effectively, it's changing. I guess that's not a good way to put it. But the first two ways were good ways to put it.
I'm resisting the urge to internalize this as just what you do. Like, I mean, it's easy to see the pattern. I mean, there's a pattern here that's, you follow it up and you follow it down. But I'll have to
picking the right patterns to internalize is important.
But without understanding it, it's sort of like when the 3 blue 1 brown, where he says, or the other way around, 3 brown 1 blue, where he wants to make you feel like you could have invented it, kind of thing.
Yeah.
As opposed to just doing it. Although I totally forget how to factor on that third line, the half AT squared. I know you're going to get rid of the squared, right?
Oh, okay. So before that was what I was talking about. I'll come back.
Well, I thought you would be canceling it because isn't ST, like ST, the final form of ST is just UT plus S0.
No, okay. So this is if so. There's kind of a hidden component here. It's like, okay, there's t equals 0. There's no acceleration in this first one.
Oh, that's right.
We're adding some acceleration. What I think I was talking about last time was when I was saying we can get rid of the t squared and also the t for that matter, is if we're working in pixels per frame and our time step is always 1, then we can do some manipulation so that we don't have to really do any sort of we can just be like 1 and 1, and we can skip that multiply. But that's just an effect of this pixels per frame thing.
Okay, fair enough.
So,
all right, well,
let's finish up
by
adding that into our code.
What should it be? Doesn't matter, I guess.
So acceleration, what we could do, gravity is acceleration. So a good one to do is negative on the y-axis and 0 on the x-axis. New vector 2. So, yeah, what I'll suggest
is... You only want to go up?
I'm going to suggest, 9.8 meters per second is a good value for gravity. If you recall from physics, that's Earth's gravity. So that's always a good one to start with. Okay. And then, all we have to do now is... you've even got that there, so that's perfect.
Yeah, cheat sheet. So I don't have to ask again. Basically, I'm just going to take this from before, which is this part, and add this. So, how about that?
That is looking really good. I'll just add that you can just kind of, I mean, yeah, it doesn't really matter, but yeah, you don't even need that extra set of brackets.
Yeah, you're right.
That looks fabulous. Shall we run it and see if that does what we expect?
Sure. I mean, I'm expecting, I guess the circle's gonna fall down as it moves forward. Or not. Yeah, there he goes.
Hey, yeah. So we have a bit of an issue of scale, but you can imagine that's a physical object, and as time moves on, it starts falling faster and faster like a real object.
Cool.
So that is basic physics. So what I wanted to just finish by is showing you couple of web pages. So over here we have the Wikipedia page for equations of motion, and this I actually don't like the way they teach this. Certainly they taught it to me in high school. Is they start with this, where I think it's much better to start with the calculus, because it comes from integrating and differentiating things, and like accumulating the acceleration and then accumulating the velocity. Using integration. But over here you'll see this formula here, number 2, is exactly what we had ourselves. They skip over the plus the initial position, but this is this formula, so that's what we came up with. But also what they provide is like, okay, here's like 4 other variants of that formula that are calculated using basically algebra from the other formula that we had. And that lets us get, it lets us say, if we have, now I had a link for this. Let me bring it up.
If you have 3 out of 5, you can get 2. That's what it's saying.
Exactly. Yeah, it says exactly that somewhere.
Yes. Right under your mouse. Yep. Yeah, that's interesting.
So what we do is we use that, for example, and in a slightly more complicated way over here. So you'll recall in River City we have this ballistics, get velocity to hit. So if we are at a position and we want to hit something at another position, and also we want to like arc up some specific amount of height. So we start here and we want to hit something here and we want to go a specific height up. This will give us the velocity to launch something that will hit this position here, given some gravity.
Right.
And so this is
all the grenade launches.
Yes, exactly. The final boss, I think, uses this extensively to get it like a 3D velocity.
Right, because he has to lob his projectiles into the world, like through the z-axis, like.
Exactly.
One of the only ones that does that is able to like push it into the world. Yeah.
Yep. So I think I looked, and I don't think the code. I think the code is not in the public stuff, but we have a few other places in the River City code that calculate just 2-dimensional lobs using the same method and the same formulas. And the other link that I wanted to show you, because we were just at it actually over here. This is update. Okay, to reach height. So that's another usage of. So you'll see this one here. This is one of these equations of motion. This is velocity squared equals initial velocity squared plus 2as. That's that one here. And so that's how we calculate how to reach the height, and then we do like a bunch of fixed point stuff to try and reduce the amount of error there. But over here is this update method. And so this is, have I got the comment in here? So this is how we do the iterative method of velocity plus acceleration. So here it is. Position equals half acceleration t squared plus velocity times t plus p to 0. So I actually haven't used the standard notation there. But
right, but that's literally what we've just done here.
This is it, and so you can see the comment there is like, as I was saying, if we make our delta time 1 frame, we can get rid of these t squareds, and so on. So our position becomes, the new position is add half the acceleration plus the velocity.
Right.
And so this over here is what I was talking about. For example, there's actually more complicated ones of these that reduce error even further. But this is like,
are these a standard thing, or is this something you have to like reducing error? Is this like a common practice, or is this something we only really are going to be doing with like pixels per frame?
It's a common. Well, it's not a common thing. So the simple way would have been, hang on, where did the code go? Over here. So you can see I'm adding position and adding velocity. So I'll have to drag that over here, and then. So you can imagine that the naive way of doing this would be just every frame velocity plus equals acceleration times time, and then position plus equals velocity times time. And so this is the naive way of doing it, but the better way to do it is what we've done here. For every frame, position plus equals 0.5 at squared plus vt, and then velocity plus equals acceleration time. And so this is like the way that you kind of get taught to do it without thinking about the calculus involved, whereas this is the more accurate way of doing it, and it accounts for this half acceleration. And so this is the difference that I was talking about over here, as you start to accumulate little errors because you're missing that tiny bit of acceleration that happens every frame.
Right, and that's the same thing as approaching zero and becoming closer and closer to the real area under the graph. That's like getting closer to the accurate
exactly value. So and you can imagine, like, okay, so like an a times t, that's roughly speaking is that, like, that's a line, whereas this one over here, it's got this squared term, and so that's going to be a curve of some sort. And so if you pretend that this curve is a line, you're missing like this little sliver of area under that curve. Like, you've only accounted for that bit, not the tiny bit in the curve.
Right. Cool.
Okay, so I think that's all of the links that I had to show you. Yeah. Okay, so I think we're done today. So thanks for watching, everyone, and I'll just find OBS to shut it off. Okay.